someone had a genius idea, thank you very much, Ashish, over lunch to throw up a diagram of the environment. So there it is. We can flick back and refer to that. I'm assuming folks are at the point where they have both network namespaces up and running. They don't have VPP running, so if you do, please stop it. And that you're good to go with, now I'm going to use Emacs for running GDB. If you want to run it from the command line, you'll see the command line, I'll stop. But we're actually going to get in and actually start debugging. So you should have, from the instructions, put into your whatever directory you're going to be using, or whatever user you're going to be using, a GDB init file. So this would have slapped that in there. It's probably, if you've gone and executed that command, yep, you'll have the correct break GDB init stuff. Where did I put the breakpoints are here. So just make sure you've got this page up so that you can reference the breakpoints and just follow along. So I'm going to copy these here. We don't want to enter these straight away. I'll explain why in a bit. So what we're going to be doing now is going through the init sequence. So we want to be doing this from I'm not going to hit enter just yet. So, okay, so if you're not using Emacs, you're just going from the command line. You basically want to be running GDB, full name, and we're going to be using the debug image, which can be found there. So assume everyone has been able to get to there. We're going to be in GDB land. So from here, I'm going to do one pass through with Unix Interactive. Now, the reason for this is, and I was chatting to Dummy about this over the weekend, if you just try and put the breakpoints in, some of the libraries aren't loaded. I'm not sure why. I tried shared library. If you have a look at the actual amount of libraries that are loaded, trying to go through and add them all individually is kind of a pain. So simpler steps, path of least resistance. Just run Unix Interactive. Make sure you get this far. From here, we're just going to stop VP or quit out of here. Just stops the process. Now, when we actually paste in the breakpoints, life is good. Okay? So no complaints about, I couldn't find this. Do you want me to put this in just in case for later? You shouldn't have that problem. So everyone should be here. Here, you've probably got to make sure that you have a couple of the helper commands that I put in. So just make sure that you can see the output from help WNM. That's okay. So this is one of the helper functions we'll be using. User-defined commands. We'll be using to dump some of the structs as we step through the debug. You should have a list of, so you help WNM, help DNR is a dump node registration linked list. You should have that as well. You know, these are the ones that were actually pulled in when you did a wget of the GDB init file. You should have these breakpoints set. Okay, so you should be able to get to, forget these first few lines. But for those who have gotten this far, quick show of hands of folks who have gotten at least this far. Groovy. All right. So from before we kick off and hit run again, if you go to the wiki, I put in here my high-level chicken scroll of init, which you can open it up with. I'm going to just download it here. We can poke around this at your leisure, but all the key parts, we're going to start off with main. And all these key parts that we'll be branching off, we have symbol-based breakpoints, right? And that's the crux of what we're going to be walking through. So this is more just for background reference. I know some folks said that they prefer to see diagrams. And again, caveat, this is just my chicken scratching as I walk through it. But that's there if you want to refer back and forth to it. We'll just go step by step through what's going on. Some parts will go in more depth than others because some parts, for example, when we talk about the heap allocation, I think if you want to go into depth on that, it's probably more appropriate. We cover that when Dave talks about buffer metadata tomorrow. Or whenever, right?
Yeah.
But for this, the point of this conversation is to really talk about the node initialization. For those that put their hands up and said, yeah, I've gotten this far, do you see something when you do help WNM?
I do.
Okay. Do you see something when you do help DNR?
Yes. It says do not resuscitate.
I love it. That's good. Okay. Who said no? Okay. So did you pull the GDB init file from the wiki? And I'll show you where. And if you did, which is fine, just one sec, dude. If you did pull it, what you may have done is it's going to try and put it in your home directory. So maybe you did it from Vagrant, and maybe you're running GDB from root, or vice versa. Just make sure you have that GDB init file.
Yeah.
And it has those help commands defined in it.
Source space file name, wherever the thing landed, that'll just suck it up for the moment.
I gotta get it first.
Oh, well, can't help you with that.
So can I just switch back, Tom? It's on the content page on the wiki, if you don't mind. Cool. So let's get started. So everyone should just be able to hit R now. And we're breaking. So I'm going to put this back on full screen because I don't need the mini buffer. Okay, so everyone should be able to follow. So you can see.
I got a different line though. So 57 to 61. I think doesn't matter.
Yeah, line numbers don't matter. They're all based on the symbols.
Ignore me.
Okay, so we're here. Now, we've initialized a vlib main t to VM to the address of vlib global main. So now we actually have a data structure to which we can refer to. So if we do help WNM, you can see that this is going to watch the node main. And I'll go through in a second what node main is and how we're going to get to it from vlib main. But you're going to want to get the address of some kind of vlib main t object pointing to node main. And so an example would be at VM node main. I like to just set it to a convenience var called my node main or my nm, and then from there on we can reference it. And along the way, there'll be various pointers to a vlib main t struct. We'll stop, we'll print it, and it'll show you that it is the same address. It's invariant, so it's still appropriate to use a convenience variable. And if any time that's not true, Dave will be the first to say, dude, chill.
Well,
it's in some threading cases, but
one
for this,
little detail you guys want to know is that the production images are compiled with minus PIE, which means that all the segment addresses will get stirred by the kernel a little bit. It's a security deal, so GDB works fine on those images once. Typically you end up just wanting to restart GDB, after you quit, simply because GDB caches symbols. You can, after beating on it for long enough, get it going again. But it's best just to quit if you're running on a production image.
Thanks, Dave. No, yep. Very, very good point.
Is it the ASLR equivalent?
Yeah. And even the shared memory segments that VPP and the vlib API portion of the exercise creates do their own segment-based address randomization for security.
Okay, so you should be this far. So from the help of WNM, this actually gives you an example of how to use it. So I use my_nm. to the address of VM pointing at node main. Okay, and obviously your address is going to vary, but you should have a vlib no main t struct. Does the output look like this so far? Okay, so now we're still in main.
What happened? Mark decided he didn't love you anymore.
Dude, can hear you. Hey, Dave. D. Barrick. Can hear you guys, you're mic'd up still. Just when you're whispering. That's all right. I don't mind, it's just letting you know. So here's our vlib main t, right, which is the VM part, the thing we just pointed to. So there's a whole lot of really useful things in here, but the thing that we mainly care about and I just generally just search, so. Sorry?
You can do a set print predict.
Here we have a pointer to a vector of nodes, right? And so that WNM thing that I'll show you in a second, it's going to spit out the length of that, right? So what are the nodes that we know about? We have a hash table of node by name. The next one, and this is really one of the key things, and when we get to walking through the graph and the thing that we'll be leveraging in our graph node, which is this vlib node runtime t, how does it get populated? Now you notice that it's nodes by type of length 4. And so there's, first of all, there's the internal graph nodes. So
Pre-input, input, process, and the internal guys, which are most of the graph.
yeah, and I think, so I was trying to do them in order. So 0 is definitely the internal guys. And we'll see that actually in the lengths.
I think that's
so,
right, yeah.
Yeah, WNM does dump each of those, vectors individually.
Hey, Keith,
Yep.
do these guys a favor and show them the Victor Lima function. You know about this one?
Yeah, it's actually incorporated in it.
Just do print VL of, mumble pointing at nodes.
Well, yep.
Yeah.
So if you, here.
It's actually a function which you call from GDB.
Yep. So you'll see here I use VL in here, which is vector length.
Yeah, which is probably absolutely goose egg at the moment.
Yeah. So I just wanted to quickly, though, run through, and we do use it. We do, so VL is Dave, maybe you can explain, because there's a number of things from VPP that we can use as GDB commands.
Yeah, well, the VL is a function that returns an integer, which you can just call from, you can call from GDB any old time. There's also, I think there's one for pool,
Here. These are right
pool
here.
elt or PEI. Okay, in Mumble VNet, GDB funcs are a set of little utility routines that are meant to be called from the debugger. Just when you want to know what the vector length of x is, just go call it.
Yeah, and so in this WNM, I'm calling VL on whatever the argument you passed, in this case the address of node main t, pointing to nodes, print out the total types, and then I just dump each of these. So you can see there's the internal is 0, inputs 1, pre-input is 2, process nodes is 3, and then I walk the next thing I was about to talk about, which is the total node registrations, and dump that. So that other script DNR essentially just does a walk of that linked list of node registrations. So if we have a look where we are in the code, we're still at the beginning of main, and we've initialized WNM, and if we dump that there, you'll see that we have no nodes.
So there are only 4 types of nodes, like pre-input, process, and is it like pre-processing, post-processing?
Actually, let me do a sentence on that. Pre-input nodes, of which there are exactly one, is the is generally the epoll wait. If really nothing is going on, it'll drop in, and every so once in a while, it'll actually look to see if there's debug CLI input. Input nodes are things like DPDK input, which actually scrape packets. The process nodes are effectively cooperating multitasking threads that run in the main thread that do things like every 5 seconds go send go send an OAM packet. That they are they're really they're really threads. They're not processes, even though it's a bit of a misnomer. And what's the last one? The last one are the interior graph nodes, which form 90% easily of the nodes. So those are the 4 categories.
Yeah. And so we're going to just be, as we walk through the various steps of initialization, dumping this just to keep a count and track of things. Yep. So we have total node registrations is 168. And there are no nodes in the node main list of nodes yet. So just a reminder of where we are. We're still in main up here.
So Keith, you did
Yep.
something to walk the constructor list?
I'm just about to do that.
Yeah, okay, cool.
So if we just run DNR against your convenience variable pointing at node under registrations, I just want to show you the actual registrations. So this is going to spit out a relatively long list. These are all the nodes that have been registered already. And if we go back through,
Yeah.
yes, it is,
Yeah.
yep.
Now notice you're right at the beginning of main, and you might be wondering how the hell anything actually happened. Well, the registrations are done with glibc attribute constructor functions,
Yeah.
so that they've already happened just before you get to main. And ditto when we get around to plugins, you'll see that before when you deal open a plugin, it's going to also go run the constructor functions out of there. And it turns out, well, I'll let Keith go. Sorry.
Yeah, so I was just about to go through that. So we have, using this command, we can dump the list of registrations. So before we go through and have a look at the macro, that as to why all these things are there and how they got there in the first place, an important thing that we might want to keep track of, because it'll pop up later when we see this 168 number increase to 169, which we will. If we were to search backwards for MaxSwap, you wouldn't find it. Why? Because it's a plugin, and we haven't loaded plugins yet. So we'll get, and I'm going to walk through that step, but let's just go and capture the first node, right? So if we walk back up here, there's 168 of these suckers, and we have the Gmon process. So if you just kind of remember the Gmon process node, something you can search on, when we see 168 bounce to 169, you can search back. We can dump the list, search for Gmon process, and lo and behold, up there you'll see MaxSwap, and explain why when we get there. But first of all, why do we have these guys here? So let's have a look at, and we'll just, since the macro is the same, where's the, I'm just going to do it.
Init.h.
Yeah, okay. I'm just going to pull this one up. I think it's in here. No.
What are you looking for?
VLibReg. So in our MaxSwap, we have this macro called VLibRegister node. Okay, and in here, you'll notice that you have the what we call a dispatch function, which is the function that's actually going to run when we want to punt things to this node. Its name. Now this is going to become important because one of the functions that gets called in our initialization sequence is to add a node by name, right? So the names become important. The next thing that you're going to find that is important is the number of next nodes, which comes from a for each loop and a macro or enums, and this MaxSwap next interface output, right? So we're basically saying that our next node that we want to send things to is named interface output. So try and remember those things, but this VLibRegister node, we're going to have a quick look at that particular macro. Just give us 1 sec, mate. I want to queue this up because it takes a few seconds. Yep, go for it.
What's the order of this node? Where do we insert this? Before which node?
Okay, so I will get to that. I'm going to show you exactly now. So the question was, what's the order of this node? Where do we insert this? Okay, so this is a macro that during compile is going to call this macro I'm going to show you in node.h. Okay. Now in here, what it's doing is passing to vlib_main_t, VM, right? The thing that we just referenced. It's basically doing a linked list operation, right? But you notice the flag here, or the attribute constructor. So we just called main, okay? So before that, the constructors all get called. So when we compile all the nodes that are part of, say, the VNet or VPP application in VNet, right? This pre-processing, right, creates that init function, that constructor. And then when we run VPP, those constructors are called before we hit main. So when we assigned vlib global main to VM, right, all those constructors have already been called for the existing internal nodes that are compiled as part of the application. So that's how come in vlib node registrations T, we have 168 existing nodes, because all the constructors are called with their registrations, and they have all the information about their names, the dispatch functions, the number of next nodes, and the next nodes by name. Okay? That's kind of an important part. Sorry, I had this thing turned off. Follow me so far? Like, this is the first step. So far, so good, Dave, or anything?
Yeah, absolutely. And another thing to say is you might want to toss what is it? Main.h, vlib.h up there so that folks see that there are a number of variants of this game that we make multiple lists of multiple different kinds of things out of constructor functions, nodes, init functions, which we'll get into in a while. Debug CLI functions. What's another example? Config functions.
Yeah.
So there are multiple list heads hanging off of the node main T. When we get into the plugin loader, you'll see that the plugin loader does a DL open, which then contributes whatever from the whatever constructor functions the plugin has, to the game at hand.
Killing my thunder, dude.
What?
Killing my thunder.
I know, but
it is awesome.
it's sort of like
Dave's done it.
If people are getting it, we don't need to, we don't need to go.
No, I'm just teasing, mate. This is all good, all good. So we'll pass through this part. So we're going to pass some arguments, as you'd expect for a normal application. Next bit is we allocate the main heap. So I'm going to skip over this. At the end, these are some of the init functions called. This VPE main init, if you saw the original pre-launch videos that Dave walks through and shows a bunch of pre-wired nodes, that's subsequently changed. And that's something I'd get Dave to walk through at the end, in that it's now more of a exclusion, right?
Yeah,
in the
okay.
SRP init.
Let me do a sentence or two on this. We switched from using VNet as a static library from which, a .a from which you pulled, kind of one from column A, two from column B, to use the restaurant metaphor, to linking against a dynamic library, for any number of reasons. One of the things that does is it says you're going to get the entire network stack whether you want it or not. And what this particular guide does is, this init functions called guy is a hash table that's used in the init sequence to say, oh, I've already called that function, don't call it again. Well, if it turns out that you set what amounts to a single bit that says, yeah, I've called it, it'll never call function X out of there. So, so the way, I think SRP, if I remember, I turned off this way in the VPP application. So the application main, rather than being, I want this, I want that, I want the other thing, has turned into, I don't want this, that, or the other thing. And that hash table is used to say, well, okay, I've called a certain function once. Well, if you say, I've already called it, it'll never happen. So that you can omit pieces of the graph depending on how they've been set up by negative checkoff. It's sort of opt-in, opt-out stuff. Nothing complicated, but just mechanics.
So does this have the output dependency? Like the interface output was the next node and the max swap. Does it, that gives it the
Okay.
order? Does it load it first? Or doesn't matter?
Okay, yeah, interface output guide, what ends up actually happening in the MaxSwap plugin when you really look at the code is it says, okay, go throw this out, the software, the transmit software IF index, meaning throw it out the particular interface. And interface output fundamentally knows how to do that. We'll walk through it. You'll see the answer for sure.
Right. And so now we've gone into vlib Unix main.
Yep.
Okay. So if we have a look at the backtrace, we can drop the back to up. Sorry. From here, right, we've gone from VPP main init and it.
There is one thing on DPDK constructor in it. You're only doing it with if it's shared memory or something.
Right. If we're using the DPDK DLL versus static linking against the DPDK.A that we've built. Damian recently added that. The idea is, as soon as practicable, we want to at least be able to build a version of VPP which will work with the upstreamed DPDK.so rather than having to compile DPDK and statically link against a version of it.
So from here, if we go to our diagram, we've gone through main, we passed VPP main init, we created this handoff structure, which is made of VNet main T and Ethernet main T. The reason is that every single plugin pretty much is going to want those two things plus vlib main init. So we set up this handoff structure, and there's actually a getter for it that we can use during the node init. From here, we call vlib Unix main. And here is where we actually start calling vlib plugin early init. So again, if we've run this watching the node main with, our numbers still haven't changed. We still have no nodes in the node link list, in the node vector, and we have 168 nodes that are part of the VNet application. As we walk through here, you can see that we're going to call vlib plugin early init. Okay, so when we jump through here, notice that we jump straight to the load one plugin, and allow me to explain. If we have a look at backtrace, we went from vlib Unix main, we called vlib plugin early init, to vlib load new plugins to here. So let me just go back up to the second frame and walk through each of these. So we went from vlib Unix main to vlib plugin early init. From here, you can see we're getting the name of the plugin path. So in our case, I believe it's user/lib/vpp under plugins. It's the directory that I got you guys to ls before to make sure that there was a MaxSwap SO in there. So here we're actually getting the directory name, and then we go into vlib load new plugins. From here, if we go to frame 1, which is calling vlib load new plugins, we walk that directory structure, okay, and pull together a list of files, and then from there called load one plugin. And this is where stuff really happens, right? So it flags it that it's from early init. And here we're in load one plugin. So before we call DL open, let's run our little handy dandy macro again. And you'll see that we still have 168 total registrations. If we just go one more step and run that again, you'll see now there's 169. If we run DNR,
that's one more.
Yeah, with the magic of television.
God.
If you want to follow along, I'll give you a second to run that. So I'm just going to dump the node registrations list by using the same vlib main T pointing at node main, which is what the convenience variable is pointing at, to node registrations. And I can go through the node types again, the P types again to show you that. But what this will do is it'll dump the entire list. So everyone good? Yeah, sorry, mate.
I don't think I ever loaded this plugin. So
Ever built the plugin? Oh,
Do you have anything in user-lib
Su-
VPP plugins by any
yeah,
chance?
sudo make install in the place you built the plugin, and then just crank it up again.
Yeah. So if we dump this, and remember our top of our list was Gmon process, we now see MaxSwap. So why is it magically there? So apologies for those who are incredibly au fait with this, I'm still relatively new to this, is that as part of DL open, when we open as part of the L file format, in the DL open, when it's going to look for that init constructor or DT under init symbol and call it just like our normal constructor. Remember the constructor, it's using exactly the same macro, the vlib registration macro, which adds it to the node registration linked list. So in that
But actually
case,
conses it onto the head because I'm a lazy guy. I'm not going to walk the whole list
Yeah,
and then put it at the end. So I just cons it on the head and point it's next to where, typical single,
but the point being, it's just we haven't actually built any of the graph yet. So by the same mechanism that we use to get all the node registrations, i.e. constructor before main, the same thing happens for the plugins. It uses the same macro, the same macro to build the same constructors, and the DL open then causes it to execute that, which adds it to the list of node registrations. Fair enough, Dave?
Yeah, yeah. The reason we do the constructor method versus what I used to do, which was actually opening the ELF file, is exactly the ASLR stuff, the position independent, the minus PIE, the thing that stors the addresses, because the ELF file has things, linked to where it thinks they're going to land. It just isn't right yet. The constructors, obviously, they had to make work, so that's why I do it that way.
So where am I? So we could walk through this. This is basically making sure that it is who it says it is, gets the handoff structure.
So the 168 ones are like inbuilt plugins. Is that what it is?
Well, they're not, there's so little distinction between a plugin and something in VNet. They're just different shared libraries effectively. And we're loading these by manually discovering them, but thematically there's so little difference between something in libvnet.so and maxswap frickin' plugin.so that the distinction's almost not interesting anymore.
Right.
And the cool thing about it is if someone wants to build a proprietary plugin, am I going to roll my eyes? Probably not even, because you can definitely imagine building a plugin and having it have a license manager or some freaking scheme like that. Fine by me. It is the way that somebody who wants to ship commercial content over this platform can do it.
So I'm going to spare you kind of going through the loops. If you wanted to, in your own time, just go next, and see us pop back out and pop back out. I'm just going to continue. And here we are back in vlib main. And eventually, we register all the static nodes, which is going to then call, while there are static nodes. So VM pointing at node main node registrations has 169 nodes in it that we need to process.
Right.
For each of these, we're going to go into register node and then go to the next one.
Yeah.
So we're going to do this once. We're not going to do it 169 times. But as we're going to register node, the key things that I want you to take away are, and we'll stop right here and we'll just dump this again, because this is kind of important. There are no nodes in our nodes list. And what's our node list constructed of? It's a p-type vlib node t. So vlib node t contains a whole bunch of important things about the node. The thing that we actually pass around in between graph nodes, though, I'm going to run that WNM again. And the thing you need to watch are these nodes by type. And inside these nodes by type, if we dump vlib node main t, right? So that's the thing that we're actually referencing to get all these counters. Having a look at vlib node main t is we have this 4 arrays or 4 vectors of nodes by type. Each of these, though, note is the vlib node runtime t. So vlib node runtime t is the thing that gets passed around in between graph, well, the parameter to the graph node, right? The dispatch function. The function that's referenced in the registration as the thing to go and call when you want to process me. And so
Total node registration should be what 169 in your case?
in my case, yes.
It's 171. So I'm just trying to understand.
So the vlib node runtime, it's very important that as part of understanding this registration process that you get what's actually put into each of these nodes by types. Because that's the thing that's going to help us understand how do I actually get from me and processing packets to the next thing, or if I have 3 different graph arcs that I want to get to, how do I actually get to those? How do I actually reference them? Because it's going to look like I'm using the next thing to me is enum0, and the next thing after that is enum1, and the next thing after that is enum2. Yeah. And how does that get turned into an actual pointer to a dispatch function? Well, this vlib node runtime is the thing, and these vectors of such things
pointer
is
to an
how
X
we
frame T. Yeah, I mean, how do you get an X frame T into which you can push buffer indices? And the truth of the matter is the distinction between the node and the node runtime is pretty simple. The node itself are things that you're not going to refer to when you're actually processing packets. The node runtime is, kind of the cut down set of stuff that a graph node needs when it's running. And it's as simple as that. That you don't need the whole bulked up thing with the string name, because guess what? You're not calling strcomp in the middle of processing packets.
Right.
If you can possibly help it.
Precisely so. And I know just from personal experience, I saw vlib node T and thought, aha, that's the thing I need to know inside out, bar none. This is the thing that's going to save me. Total brain fart on looking at the graph node and seeing the most important thing it gets past is vlib node runtime T. Couldn't work out how the hell do I get from enum0, how does that actually reference the next arc, right? It's all in here. And it's all in this step we're about to take, which is the register node. And Dave, you're really going to lean on you here, because
I'm going to go for it.
I'm kind of a little bit frazzled because things haven't been quite going to plan.
Well.
So bear with me. So we're inside register node. Now, just for laughs, I won't try not to say shits and giggles because that would be unprofessional. We're still at 169 nodes, and we haven't put anything into our 4 vectors of node runtime T's, and we haven't added anything of type vlib node T, which is the first one. And good point of order for next time, I'm actually going to update if these macros, first of all, are these kind of macros, these helper functions, are these useful for you to kind of see what's going on, to summarize the state? Because what I might do is actually change them to actually say the types, like the actual type defs, and put them in there. It might be a little more helpful and descriptive. I'm just saying nodes, 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 nodes. How I say nodes 3 times there, and none of them are actually any more descriptive than the other. So let's go through this. So we're just going to skip through the clib debug stuff. Here. Now n is of type vlib node T, right? So again, that descriptive structure of the node, but not the thing that's actually the runtime. But so n is of type vlib node. So we're going to create one of them. So typical mem set. Now n index. So what is my index? So the index is kind of like the identifier for the node, numerical identifier for the node that's created at runtime, so unique to the runtime instance, right? So how do I calculate that? I take the vector length of nm nodes. Now, what is nm nodes? And again, if I actually had the type here, you'd see it'd be length 0. So it is going to get index of 0 because it's the first node that we're processing out of that list. Now, so yep, trucking along. Then we do a vecadd1 of n, which is our new node, where we allocate some memory for of size vlib node T, and we add it to our nm nodes vector. So if we were to do wnm $my_nm, we see that nodes is 0. If we pop over this sucker and do it again, nodes is now 1. So we've now added something to our vector of nodes. But we still haven't updated the runtime, right? And remember, the runtime is the most important thing in terms of graph processing. I saw an aha moment. Is that a nod? Yeah, cool. Win. It's always nice to get a
Keeps
small
going.
victory.
We'll be doing this for 3 days before we get to 169. But I know he's not going.
And we're going to go through each and every node. So
Could you just summarize the top level? What are the goals of a node registration?
Well, the goal,
Okay.
the goal is to correctly set up the vector of next indices such that you can actually push packets forward in the graph, and to make it so that how would you put it? The data structure that the graph dispatcher uses in its main while one loop that you're going to get to presumably before this peace in Palestine or hell freezes over. So that the graph dispatcher can actually dispatch, run the dispatch function when necessary.
yeah.
We're going through a lot of bit level detail once, which if you've ever seen this, you'll kind of the hope is that you'll kind of remember it well enough to know. All right, here's all of the real low level stuff that goes on, but it's rapidly going to get up out of the weeds.
Yeah. And that's a hint. So I'm going to scooch through this. So
Yeah, and obviously you might want to be able to find a node by name, so you go hash set into the node by name hash.
Yep.
This guy and the node index.
now, save the index in the registration. So we just allocate an index, and we're going to update the registration, which is the 168 list.
Yeah.
Okay, or 169. Same thing, we take the function. Remember, that the 169 list is the thing that contains the information from the vlib registration macro. One of the things is the name of the dispatch function or the dispatch function itself. Now we associate that to the node. So we're now just copying information over. This macro just simply copies information from the registration to the node, so on and so forth.
And notice in regular packet processing, vector size is always basically 4 bytes. That we're doing, U32, and it'll turn out that the elements in the vectors are all going to be packet indices, not pointers to packets. One of the things, to put my hand up and say to the DPDK guys, is that you save a tremendous amount of width in the stuff that you're pushing around by any chance you can, figuring out how to do indices or offsets or handles which are less wide than 8 octets. So that, if you think about 256 by 4 bytes, that's the amount of cache pressure you're not putting on by making, by using a 32-bit handle for a packet rather than by using a hard pointer to it. And that gets significant. You're just trying to tune down the number of spurious cache misses you're taking.
Mm-hmm. And so then the next thing is we want to register the errors. So when you see show errors and a whole bunch of counters on a by node basis, this is where we do that.
Yeah.
Elog is event logging and event log initialization. That's not syslog, that's event log. We're going to get to that this afternoon. Dave's going to go in great detail. He's got some really cool stuff to show there.
Okay, this afternoon. Okay, cool.
Yeah, dude, it's still early days. We're going to be here all night.
Be
Okay,
all-
now the runtime. I'm going to scooch through. So we're just going to copy data bytes for the runtime, do a vec resize based on r n number of next nodes to the next node names, making sure that the next node names is the correct size.
Yeah, for all you
Okay.
DPDK guys, the runtime bytes is the exact analog of the RTM of private data area. It says in the node runtime, give me this many extra bytes so you can stick whatever you like there.
Init, empty, vec validate, we've kind of covered those things. This is interesting, the n owner node index to set to twiddle 0. So twiddle 0 you're going to see quite a bit as an initialization or a flag to say it's not null, but it ain't got real data yet that we want it to have. It's something we can capture and if on.
Yeah.
Okay, so now we're going to sorry, go ahead,
In
Dave.
a world where you're using a lot of indices, 0 is a pretty good index in a vector. Twiddle 0 is extraordinarily rarely a good index in a vector, although it could happen. I don't want to go into a long diatribe, but you'll very frequently, see things set to all Fs or twiddle 0 as a means of saying this is, these are not the droids you're looking for. Move along.
So here we get to initializing the node runtime. So I'm going to ask Dave to stop me when we reach a couple of key bits, especially the bit where we take the enums and the list of node next names from the vlib registration T constructor of the node and whack that into the array by types.
Yeah.
So, because I've covered this, I haven't memorized this code, but this is the bit that helps us jump from arc to arc or node to node via arc using simple enum 0, 1, 2 type offsets. Yeah,
Yep.
Dave?
Yeah, close enough.
So-
Yeah, and this is a little bit of drama around running over a non-4K page size. This stuff, VPP has run on AArch64 little endian with a kernel compiled for a 64K page size. So that was a little bit of random drama, but it is one thing that I needed to fix up. Okay.
Okay, so we're going to process the node's runtime index. Remember, all these indexes, we take it from the vec length, so they're all runtime, right? They're not statically configured as here's my node index
Yeah.
or my node number forever into the process
Yeah.
pointer vector. And we vec add one. We've now added the process.
Right.
Not sure what that is.
What
Here.
is?
The pstack0 vlib process stack magic. That's more of page
that's
protection
a
stuff.
stack. That's a. Okay, the threads don't predict.
Yeah.
Did I bother setting up a guard page for processes? I bet I did. But at any rate, that's the Stack Overflow guard, which it checks.
Yeah, you did down here if def clib
Yeah,
unix the m protect.
okay, yeah, and mumble, this stuff could run elsewhere, but we protect one page at the bottom of the stack. So if you hit it, it's very much like a pthread, blah blah blah. You'll get a fault and it'll stop. That is not 100% perfect. I've seen cases when people have put gigantic things on a stack. The process stacks are sized through the node macros. There's a log2 mumble stack size guy. Very, very often they're run with pretty small stacks, 16 or 64K, because typically you don't need much if you're not going into great depth. If you're sitting in a while loop processing events, you don't need to go very deep in the stack there. So the stacks on the process, the cooperating multitasking threads are set real small. You may, for a given one, have to bump it up. The guard page is to keep you from hurting yourself, if possible.
So here's
Now,
where we, sorry.
Yeah, this guy is a lot like, I have a vector of, in this case, 4 packets, and I'm dealing each one of them into a different slot. The reason you're computing a different runtime index to the node index is exactly that not all nodes are of type 0, so they're getting dealt into this node by type dude.
Yep.
And I think that may have been what Keith was wanting me to explain a little, is why are we doing this?
Yeah.
In distinction to the node index. So that at any rate, that's the explanation. Is there are at the moment 4 classes of nodes, and the runtime for the 4th process the runtime index for the 4th process might be 4, whereas the node index might be 75. So it's different numbering space. That's it.
Now, because we've assigned that inside here, we can do this to get its index as opposed to a pointer to it. So this is the pattern Dave was talking about before, where we take
the
thing and subtract the head of the.
Yeah, because vecadd2, eventually nm nodes by index by mumble type is going to expand, and you don't want to be memorizing pointers. It's the typical vector pattern.
So this is how we update the runtime index. We take its value minus the head of its vector, and that's going to give you its index in the vector.
Yep,
And
got
so
a
the
mic?
question- What's the difference between the 4 different node types?
Input, interior, and process. I think I went through this once, but they just have different functions. Some of them are polling to get input from a hardware device or from an accelerator or whatever. The type 0 nodes, the interior graph nodes, are the ones that are scheduled and dispatch packets. Pre-input node, there's really only one. It's the ePOL. It's the ePOL thing that watches for console I/O or socket I/O. And process nodes are those cooperating multitasking threads that we've been yapping about.
Yep. So inside node.h, vlib
Yeah.
node.h, search for internal.
Yeah.
And
Internal
in the
0.
comments, it gives you a description.
Yeah. Yeah, that comment about clean out TX driver, TX rings is historical. I should probably douchebag it.
All right.
What's my phone want?
So now we've updated the runtime index. Again, updating some counts, copying some information across from the node, which is vlib node t, to the vlib node runtime t, setting the number of next nodes into its number of next nodes. Now, next frame index. The next frame index is set to node, the length of node main's next frame, so the next cab off the rank in terms of that vector. And then we do some resizing. The frame gets initialized, some resizing for errors, and then we free the thing that we no longer need. So now we've updated our runtime node with all the information from the node itself. It's aligned, it's inside its a correct structure. It has all its friends in terms of its next nodes. When you look up those, and we can go through an example later on, because it sounds like we're reaching to get onto the next part. I can show you, for example, with our max swap. If we were to have a look at max swap, you'd see that its next node is interface output, which was in the vlib registration. It's going to spit out its node index. If you then had a look at node main nodes indexed by that number, out would pop the node for interface output. So that index along the vlib runtime t arrays or vectors has pointers pointing back to the actual node, which is the next thing. It has a pointer to its runtime index. Voila, you now have all the information about its runtime, because that's the context that gets passed as a parameter to the graph. So just jumping back over here then. Where are we? Covered all this, so just continuing. Now we go back to our register node. Again, this is just going to loop through. If we were to continue here, we just keep punching back to here. So just going to disable 8. And then from here, we're now calling the init functions. So, whoops. Init functions, these use a similar kind of game in terms of vlib underscore register, which is a macro is the init functions that you can see.
It's another constructor linked list game. This time it's to set up fundamentally tables that the graph nodes you just created statically are going to walk as much as anything. In other words, here's how we go build the graph, and here's how we go build the supporting tables. And the init functions are largely concerned with supporting tables. Mm-hmm. That was actually a good sounding story. I don't know how true it is without thinking about it a little harder.
So this vlib node add next with slot, we're probably not going to, sorry? Yeah,
this is a good one. Yeah. The thing here is that in the node runtime is a vector of next runtime. Let's be formal about it. Indices, and this guy says, "Oh, do I have an arc from A to B? If I already do, here's the arc you want to use." That it's quite possible to repeatedly say, "Go add me a graph arc," and you're always going to get the same answer once it's been created once. This is convenient if how would you put it? You can just rather blindly go adding graph arcs, and you're not going to suddenly blow the vector up with a million redundant copies. It'll just keep giving you back the same arc. And there are times when you want to do that. Mm-hmm. Or when you don't want to think very hard about the problem. It'd be another way of looking at it.
And do we want to walk through this or just scooch along? Right?
Ikimashoka.
Sorry?
Ikimashoka.
I'd like to say you speak in my language, but it's been a while since I did that. So same game, vlib node add name next with slot. It might be quicker just to have a quick look here. That seems to be reasonable. I can probably blow it up a little bit more.
Well, it blew up pretty good. Now we got nothing.
Huzzah.
Yes, transparent image with a black background.
Yep, that's a win. Good point. Thanks. So we've already gone through vlib plugin earlier init. We are vlib load new plugins. We've gone through here, and we were just walking our way through register node. and you'll see this is a linked list walk. What we're about to walk through, the thing I wanted to show you is, when you call vlib node add name next with slot, it'll go through and you can probably walk this code yourself. You're more than capable. But here we actually, from vlib add name next with slot, obviously we're going to try and find the name and then call vlib node add next with slot. As we go through here, you'll see that it recurses through after calling through next. So this is part of adding the graph nodes into that runtime as well, and that's called from here. And then
one warning about the graph hookup is if you see messages, node A can't find successor node B, just go figure out why, because the next thing that'll happen is you'll try and push a packet, and the entire graph is broken at that point in the game. If you start seeing I can't find a successor node, it's real easy to typo them, and in a production image, it'll just the image won't even crank up. In a debug image, so that you may be able to make some progress, it'll crank up. But the second you hit the graph with a packet, it's going to crash. Probability 1.
Mm-hmm. And so you'll see now if we run this, because I spared you going through 169 iterations. All our nodes are here. We have 147 internal. This is the accounting stuff I was talking to you about. I'm not exactly sure why these don't add up, but it could.
Why what doesn't add up?
147 internal, 8 input, 1 pre-input equals 156, but we have 169. I'm not sure if any of those nodes get accounted for in there or.
Remember what I was saying about negative checkoffs?
No.
Let's see, node registrations. Let's go figure it out offline.
Take it offline.
Yeah.
So it's probably my bad in the macro.
Yeah, could easily be my bad too. Oh, you know what it could actually be is you mumble. Yeah, we should go work it out, but clearly isn't functionally much of a problem.
No.
Yeah.
So I'm just disabling breakpoints 8, 9, and 10 just to speed things along. Get back to our vlib node main T, and we've already gone through all this of resolving names. We'll probably skip through this part, and everything's come up. And if we do show vlib graph,
and you have a real tall screen.
Yeah, you're going to get a lot of output. And so this show vlib, I'm just going to get to the top so I can at least get the headers. It could be here all day because it's rather large.
Search backwards for the GDB prompt.
Yeah, good point. Hey, someone's done this before.
Oh,
always, yeah. Sorry. Thanks, mate. Who's the rookie? Okay, so from show vlib graph, we had the name of the node, its next node, and the nodes that called it the previous ones. From here, hopefully searching forward, if we look for max swap, we'll see that.
Keep going. You're not at. Yeah.
Max swap. So interface output can be called from max swap. Max swap can call interface output.
We haven't really hooked it up to anything just yet.
I was going to say we haven't enabled it. I was trying to think of the right way to say, well, what are we missing here?
Yeah. Now,
and that's haven't made max swap a next node of anyone yet.
Yeah. The point with the max swap tutorial is no two graph nodes of any sort are really exactly alike. Otherwise, why would you have two of them? And max swap, what it does is it uses a driver per interface redirect feature to collect packets directly out of the device driver without any great amount of pre-processing. And as a result, there's a little bit of debug CLI and also an API to enable it on an interface. And you're really never going to see a static arc to get you there.
Right.
On the other hand, it does end up with arcs to the interface output guy.
Yeah. when we enable it. So
Yeah.
I'm just going to pause there. If you go through this in your own time, like there's various bits that certain people find interesting and others will find more interesting, and you can kind of step into things, step over things, continue, fin, what have you. By and large, if you use those two things, the dumping of the node registration so you can see all the nodes that we're registering, and if you watch the node main and see the counters kind of increment at various steps, and then really understand that runtime type that gets created in register nodes, that's really how all the graph gets wired together. And that's the thing that we're going to be leveraging in the max swap to say, my next thing is interface output, and show how it dispatches packets there in terms of a, God, I'm mental blanking, just presumptive enqueue.
Yeah, the
Speculative enqueue, thanks. And things of that nature. All right, so I think what we'll do is, if there's no major questions, the point is you have all the tools now, right, in terms of the breakpoints I think are important, a couple of cute little macros to kind of dump things at various points along the way, and a little bit of a pointer into really focus on the vlib node runtime T to understand how the graph is constructed, enough to go back and kind of play around with this yourself and really dig into it. And I think we'll take a break unless there's any major questions, give Dave some time to talk about event logger, and then we'll get into probably call it a day after that and get into the actual graph node first thing tomorrow morning. That's all right?
To really walk, it's fine with me. Yeah, the other thing is, do folks have, before we break, do folks have questions on the setup stuff? Just go for it.
Yeah, I think I understood the exit.
You want to grab a mic so this?
Yes,
yep,
please.
thank
Thanks.
you.
I guess the exit from a max swap to the output, interface output.
Yeah.
Now, in case of max swap, you said it attaches to the interface and gets packets directly, like as an entry function into max swap.
The entry into max swap is done in connivance with the device driver. Keith, do you just want to throw the debug CLI up there, and we'll show you the API that's used to say, I want, hi, I'm a graph node, I want all the packets from an interface. Again, there's probably about, a St. Thomas Aquinas' worth, meaning 7 different ways of hooking nodes into the graph. This one uses a fairly special purpose one that says, I want right of first refusal on packets from the device driver on a particular on a particular physical pipe. So if we go look at, it's probably literally in like maxswap.c in the plugin.
I like him, yeah.
Yeah, you just might as well show them the code because there's nothing mysterious about it. Yeah, and just go look for redirect would be the word I imagine I use knowing me. Yeah, there you go. Okay, see this puppy? This is saying, modulo, please give me a VNet main. Software IF index is the interface handle. Node index is the max swap graph node, and node index. Where do we get it? Oh yeah, there we go. Notice this little game where you say, if enable disable is true, actually use maxswap node.index, which is that node registration T thing you saw the node hooker upper actually populating. This is actually in the node registration. It's not in the runtime, it's in the registration. And it turns out this guy's basically saying, look, give me all the packets from that software IF index and hand them to node index or twiddle 0, which turns off the redirection. So this is an action function that's called under some debug CLI, which is the next screen page. We'll get into this in more detail, but that's kind of,
in this case, it's special, but in a general scenario.
Okay, in the general scenario, let's go look at, back in the show vlib graph, Keith, let's go look at how about IP4 forward? Or IP4, how about IP4 lookup maybe? Because I know IP4 lookup, is going to have plenty of guys that'll enqueue junk to him. Yeah, you want to actually go, notice, not map. Yeah, it'll be there somewhere.
Here we go.
Yeah, there. There you go. Okay, so now this guy has quite a number of arcs leading. Quite a number of arcs leading away from him. Those are successor arcs in the graph, and IP4 lookup, if you do a research project, who can call him? Well, there's even a larger set of guys that can call him. Where, for example, if you're doing a tunnel encap, it's quite common to encapsulate it with a rewrite string of 4500, 00, mumble, mumble, with the checksum, and then you go throw the packets at IP4 lookup. It'll then do the lookup and forward them. So you have quite a number of ways of getting to IP4 lookup, and quite a number of places that things can go after it. That's the more general case of an interior or an internal node in the graph that's getting traffic from a bunch of places and sending it to a bunch of places.
So in this scenario, those nodes or the nodes in the graph would define where they would, and that's how they will get attached.
These are ancestors, and these are the places that IP4 lookup can send packets.
Yeah, so those are like more exit, and that's like entry.
It's exactly node name, can send traffic to, gets traffic from. Those are the three columns in
So
this
then
list.
this node doesn't decide where it gets traffic from. Those nodes decide where they send traffic.
Yeah, exactly. That it's sort of you decide where you're sending stuff, and other people will send stuff to you.
So if I have to insert a node in between couple of nodes, then do I have to modify the other node so that it can send to this?
It varies by where. For example, if you want to interpose something in IP4 lookup before IP4 rewrite transit, it's going to turn out that there are tables that this guy walks which actually have essentially these magic numbers in it, and you can say, oh, call vlib node add next the slot. You then set up his tables correctly, and son of a gun, all of a sudden IP4 lookup is going to send packets to some absolutely brand new thing. That there are not many places where you actually have to do brain surgery and go change the way the graph really is. You can augment it and build data structures to cause things to flow. The classifier is a perfect example of a place that just set up and begging to say, oh, hi, I'm a session, I just hit in the classifier. One of the fields in it is, okay, what's the next index off of the classifier node that just walked the table?
Okay, so no, the point I was trying to get into, if I'm writing a plugin independently, I still have to go in and modify the register of the node who is going to send packets to me.
Yeah, it's very typical in a plugin to do things like register to grab IP4S UDP to a particular desk port. If you want to do a protocol that's not there, that's the particular registration. It's case by case. Okay. I can imagine needing, for a certain class of plugin, if you want to do something that we never thought about and we never really built a degree of freedom into the table walking, you might need to modify the main line. But that activity, it's not a real common thing to do that. I add features fairly frequently, and it's not real common to have to go screw around with 10 other places that are already there. One thing I'd say is if you're building core protocols, you can build them as plugins or you can build them as part of VNet. The reason for building a plugin is, frankly, build convenience and packaging convenience. It's not really thematically different to building stuff right in VNet. So if you push a change that's not doing anything insane, of course, nobody's going to push back about it. So it's all case by case. I mean, if two graph nodes were the same, they would be one graph node.
Right.
Thanks.
Yeah, just follow up on that.
Let's say I have NAT. NAT is one feature, followed by, let's say, TCP intercept or something.
Yep.
I need the NAT to happen maybe before TCP intercept in one direction, the other direction, right?
Yep.
So there's ordering is very important.
Yep.
So what you are explaining, I thought was looking very simplified, but I need to take care of the ordering that this has to come before.
One thing to say is if you look at the at the IP4 and IP6 fib setup, there's actually an ordered set of features that can be configured on or off. Again, there's 20 games that you can play to do that. Really, it's a matter of decide what feature you want, decide where it has to run, exactly where in order it has to happen, and then either say, oh yeah, well, here's the exact place I need to name it, or fundamentally, call up and ask, send an email, because it may well be there's a really simple way of getting the effect you want, or maybe we have to make some structural changes. Again, the stuff is fairly well worked out, but not every possible combination of ordering constraints and building the table so you get them kind of without touching anything. Not every possible combination is satisfied, but you just let us know. You know, the stuff is easy, is real easy to change. The things that make me crazy are changes right in the speed path where I know they have to be done exactly right. Generally, adding a feature off to the side that hooks itself to the, to the IP, IP UDP local path. Okay, that one feature could be slow, but the chances of it having, a blast radius of the entire thing and, getting, really, majorly hurting performance everywhere just because it's kind of slow is zero. If you go right in the main IP4 fib lookup and rewrite path, those changes have to be very carefully measured. And Maciek, wherever he's hiding, will, undoubtedly be telling a long story about the performance lab because really, VPP has been getting faster, not slower, over the last decade. I mean, when I started off, we could just about fill a 1 gig E, and now we're doing a pretty good job at filling a 40 gig E. So it's continuously improved in performance, and we mean to keep it that way. But to add a feature that isn't there generally doesn't require brain surgery all over the place. It's one of the trade-offs in building a Swiss Army knife that's easily extensible versus building a pipeline that's absolutely tuned to one workload and never to do another workload. That's kind of where we're at.
Yeah, the only thing which I'm kind of worried about is NAT, because I want a state before the IP address in the translation.
Yep.
Because I'm seeing the packet coming.
Well, a really, if you want to say that, packets aimed at a particular subnet need to be natted, a really good thing to do is add an IP adjacency that says, oh yeah, by the way, don't start rewriting the packet, just go over to the NAT engine. That's how without thinking about it very hard, that's how I might choose to do that. I might also choose to just steal the packets off the wire. Notice if you steal packets off the wire the way the Mac swapper does, you're not getting at that point in the game, source RPF check, TTL decrement, any of the stuff that you'd expect IP blah input to do.
You want those things to be run.
If you want those things to be run, then what you do is you go put into the set of configurable features which are mentioned in IP4 forward, IP6 forward. There's just a list. That's the order. Put your feature where it needs to go in that ordered list.
So that list is in which file?
It's in IP4 forward and IP6 forward. I can show you offline. If send me an email and I'll send you the pointer.
Okay.
That's a
It's a deep one to get something.
Yeah, it's the kind of thing that takes me a while to get working because I don't do it real often, and yet extending, adding a feature is really not hard. Adding L2 features is a little different than adding L3 features.